Okay, so let's take a look at gravitational potential energy. We've already talked about gravitational potential energy with this equation, mgh, but this is only true if the object is close to the surface of Earth or at the surface of Earth. As the object moves further and further away from the surface of Earth, so as an object were to increase in altitude, the gravitational potential energy of the object would decrease. So let's just recall how to find acceleration due to gravity on a planet. So we set both of our equations, force of gravity equal to force of gravity. We recognize that our mass of our object that we're looking for cancels out, and we get acceleration due to gravity is equal to our gravitational constant times the mass of the planet divided by the distance between the two objects, the planet and the object, squared. So if we look at a satellite, the satellite's going to be our object, above Earth, and we want to find the potential energy of this satellite at a distance, so it's not right at the surface of Earth. Let's start with this equation. Our equation we already know, potential energy, gravitational potential energy equals mgh. H in this case would be our r, distance, so mgr, and based off what we solved for g earlier, which is gravitational constant times mass of the planet over r squared, if we substitute that in, right here, we notice we get m times g, mass planet over r squared, times r. Our r's cancel, leaving us with our new equation for gravitational potential energy at a distance. So this will work always. It is g times m, our object, times our mass of our planet, over r. So the only difference between this and our force of gravity is there is an r squared quantity in the denominator for our force of gravity instead of just r. So m is the object, mp is the planet. So let's do an example problem. If we have a satellite, it's circling Earth 500 kilometers above Earth's surface with a mass of 800 kilograms. We want to determine the following. A, the force of gravity between the Earth and the satellite. Let's start with that. So we know how to do this already. F of g equals g times mass of the satellite, mass of Earth over r squared. Let's plug in what we are given. We'll notice that we end up getting 6,787 newtons. We want to make sure we add both of our two distances, the 5 with our 6.38 times 10 to the 6th, the radius of Earth. And now we're looking for acceleration due to gravity at that 500 kilometers, so above Earth. We know that acceleration due to gravity at the surface is 9.8 meters per second squared. So if we're 500 kilometers above Earth, we're going to expect this value to be less than 9.8 meters per second squared, since it's not right at the surface. So just like before, if we have our two force equations, set them equal to each other, our mass of our satellite ends up canceling. We're left with g equals gravitational constant times the mass of Earth over r squared. But when we solve for g, we end up with 8.41 meters per second squared, a value that is less than our acceleration due to gravity when we refer to the surface of Earth, which is how we've been solving it thus far. Let's take a look at C, the gravitational potential energy at 500 kilometers above Earth. So let's start with our equation that we derived earlier. Gravitational constant times mass of Earth times the mass of our object, in this case the satellite, all over the distance between the two objects. If we plug all those numbers into our calculators, we should get a value of 4.6 times 10 to the 10th joules. Well, let's double check this with what our equation, the equation we've been using so far in class prior to today. So gravitational potential energy, we used to write it as PEG, P, capital E, subscript G, but this is the same thing, capital U. I want you to get used to that because that's what's on the formula sheet, equals mgh. M is our mass of our object. Our object in question is the satellite. So if we multiply our 800 kilograms, mass of the satellite, times the gravity that we calculated in part B, 8.41, times the height or the distance between the two objects, so our 6.38 times 10 to the 6th, radius of Earth, plus the 500,000 meters, the distance above Earth that the satellite is placed, we'll notice we end up with the same value we just calculated, 4.6 times 10 to the 10th joules. Okay, density of Earth. You might be asked to find the density of different objects on the AP test as well. So let's just make sure we know how to find the density of something. So density, rho, I have another Greek letter. So rho is equal to mass over volume. Density equals mass over volume. Well, here, rho is density, m is the mass, and right now we're finding Earth, so it would be the mass of Earth, and v is volume. So in this case, it would be the volume of Earth. Well, the Earth is a sphere, so we're going to need to know how to find the volume of a sphere. And our equation for that is 4/3 pi r cubed, specifically Earth, so the radius of Earth cubed. Plug that into our equation. Well, our mass of Earth is 5.98 times 10 to the 24th kilograms. And our radius of Earth, 6.38 times 10 to the 6th. Make sure we cube that. Plug this into our calculators, do a little number crunching, and we're left with 5,497 kilogram per meter cubed. That is the density of Earth.